you should see it now. So new things going on. We took exam 5 on Friday. We graded those over the weekend. You should be able to see the scores on Canvas and on Gradescope, some more added information on perhaps why you missed something here or there. Overall, the scores still looked probably on average 5 or 6 points higher than normal for an exam, which is good. Not quite as high as the 85% average we had last exam, but also with the large majority of the class falling in and a pretty nice distribution in the A to C range, this is probably not far off for where we want to be. I also have posted the solutions to exam 5 and made a video commentary about the exam on YouTube, which could be useful. There's still a couple questions that were missed on the multiple choice that I want to review briefly in this class, just so that everyone at least can get that feedback if you don't watch the video. I posted a sort of general final review. There's blank slides and also ones with things written on it on Canvas now. And I made a video that kind of goes through the first 4 topics. I did the first 4 just because those are the farthest back, and I thought people would want to have some refresher on that the most. Mainly, we just kind of talked about the different contents that are on it. A lot of the lists were the same as what you have available to you on the full topic list for the final. And I worked through some representative problems that I think hits on most of the key points, or at least some of the main points from each topic, just to kind of remind the types of things we were learning at the time and some of the reactivity trends. And since a lot of people still have questions about sort of general acid-base chemistry, how to determine that, I went and took every single, I think, multiple choice acid-base problem we've had on any of the problem sets in exams, and I put them into one document. That's on a blank one's on Canvas if you want to look at that and try to work through the problems yourselves. And I also made a video explaining answers to each individual one. So if there's specific ones, you should be able to kind of skip ahead on the YouTube video to find out which one you might need help on. Hopefully that is useful. Oh, I also made a reaction summary. I'll load that up. I think I have that. Yeah. And so this, again, just kind of goes through, I think, all of the different early reactions. Some of these are reactions from Organic 1, 2310, 2311, and they have some commentary. So like, not only does it show you the overall reaction, might give you some general ideas about how to choose where a nucleophile comes in. Like when we have a bromide in the dibromination, it will want to attack the carbon that stabilizes positive charge better. I think this hopefully will end up being, again, pretty useful for going back through some of the reactions. I tried to get most of the reactions we talked about on here in some form. We got topic 2 here pretty well. I did notice, like, I guess there's not a exhaustive list of conditions for reducing a nitro group, but those would be summarized, I think, on the slides already pretty well. And also I have them listed out on that topic sheet. But again, this should provide, I think, a very good framework to go and approach the final for reviewing. I accidentally have, I guess, these olefin-making reactions twice. Couldn't hurt to see them again. And there's some, I guess, overlap with maybe some of the topic reviews that I had made for the last 2 exams, especially maybe in the enolates, but I think there's some slightly different commentary. I just uploaded a newer version of this onto Canvas because I noticed I have a line on something else. I borrowed some of these from another class, an advanced organic class where we talk about more things, and there's a line I forgot to cut out, but so if you see something about a weinrod-amide, we have not talked about that at all, and I updated it there. So hopefully that's useful. One thing I was thinking, because people are asking me questions about the extra credit, and I was just going to have it be available for submission until the final. But then I can't really post solutions to it without people being able to just sort of copy the answers and upload it, and I did want people to at least try to complete it independently. So I was thinking maybe if we move the due date up to Wednesday midnight, that still gives you guys several days. Again, these aren't going to be graded other than making sure it's not like a blank document or something with clearly no attempt to answer the question. So even if it's wrong, but you made a valiant attempt, I think it'd be better for you to submit something that is slightly incorrect and then being able to at least see the answers on the other side. So that at least I could get those up, posted just after midnight. So I guess early Thursday morning, and I could have that automatically there to upload so that people could at least go and review and maybe check some of their mistakes. So unless someone is strongly opposed, I will go ahead with this plan. I think this will benefit everyone better. If you have a strong argument for why you won't be able to do the extra credit until Thursday day, send me an email. We can probably work something out. Yeah, people like, I think, having the answers in one place to review, and I think that's probably it. So the extra credit, I put it in the email, so it'll be 10 exam points. This does not mean 10 percentage points added to your exam average. This will be 10 points like added to a single exam. This would not be added to the exam of that is dropped. We're still dropping an exam. If I did my math right, essentially this will just correlate to adding 1.5% to your final class score, if you want to view it in percentage points and actual impact. So if you had, a 74, it would go to a 75.5 in the class, which I think. So you can also view it maybe as adding a 5-point curve to each of the last 2 exams that we had that were virtual or something. However you want to think about where these points go, that will be the impact at the end of the day. For more information on the final, I'll get the templates for the final up later this week, probably Wednesday, if not, definitely by Thursday morning. And the final will be roughly twice the length of a normal exam. It's going to have 16 multiple choice, 8 fill in the blank, 2 mechanism, and 4 synthesis. So this is almost exactly taking the exams you've had for 4 and 5 and doubling each type of question. There is one question that I'll have on there that I already know that's kind of somewhere in between a multiple choice and a fill in the blank, but you will see, because there's a component where you can kind of choose and there's a component where you'll fill it in, but it'll still be in this sort of box system. So, and I think it's a good question. The final will be uploaded and turned in exactly the same way as the other exams on Gradescope. So we'll have a submission there. You'll just have a longer period of time to do it. I think this means, this I think will still happen in, well, not the normal class time. It'll be in the normal final exam time, which is a 3-hour window on Friday. I'd need to check the exact times, but I feel like it's kind of late morning when it starts. I can look on my calendar real quick. I have it on there. Yeah, the final exam looks to be from 11:20 to 2:10. We'll probably go by that. So we can probably add another 10 minutes onto that if you really needed it for submission. That way it gives you a clean 3 hours. Since I think with this exam, I would expect to take definitely less than 2 hours to complete in a normal, compared to the normal time we work with. So you should have an extra hour more than you normally would, or 30 minutes more for a normal test relatively. So I think it should be good. I never said there was going to be a multiple choice on the extra credit. I said that it would have questions that were representative of the final and would involve multiple sections in a single question. And I did this mainly because if you want to have more questions, I feel like most of the other questions on the final largely are localized to one topic or something similar to what you've seen before, where maybe you have to do a Friedel-Crafts and then use it in another reaction. I feel like these are the ones that are going to be maybe a bit more complicated, so I wanted to get a feel for blending a few more different reactions together. And the synthesis problems will usually require probably concepts from 2 different topics kind of combined. I think in some cases, like if you've looked at it already, it's pretty clear that you need to use the malonic ester synthesis in one of the questions, and then at the end it'll need a little something else. But yeah, overall, people usually don't do significantly like worse on the final or anything in this class. Usually that is either this exam 5 or exam 3, I think are usually the two lower scores overall in the class. So, I mean, I would still prepare and study, but usually this is not something that ends up hurting someone's grade significantly, but view as an opportunity to improve. All right. Do people have any other general questions about the final exam before I just cover a couple different questions quickly from the past exam? I don't see anything. But yeah, so we're going to make Wednesday midnight, and I'll change that on Gradescope so you can see it. And so I'm just going to go through three multiple choice questions and then one of the synthesis just to mention something that I think I probably didn't cover clearly enough during the class. So these are the three multiple choice questions that were actually had people miss the most. And this reaction is the deuterium hydrogen exchange. Just one thing I wanted to mention is that if we think about the pKa of something like deuterium oxide, that's going to be about the same as water. So we can say like 14. If we think about the pKa's of any of these hydrogens on the benzene ring, these are going to be really, really high pKa. We're talking at more than 45 probably. So hydroxide, or in this case, deuterium oxide, will not be able to deprotonate one of these aryl hydrogens. So I think one way to kind of look at this question is get rid of all of these options pretty fast. And I discussed this a bit more in the video, but then we kind of have two options left over. One is A, that still has two hydrogens next to the carbonyl, and everything in this section, we know that these will definitely be exchanging. So through a process of elimination, we potentially could get to the answer E pretty quickly. Whenever you deprotonate alpha to the carbonyl, we make an extended enolate. And that means that we can move this charge either to the alpha carbon or all the way to this gamma carbon as well. I'll just write it as phenyl to save space. And this is how we're able to get to all three of these different sites. So we won't actually be deprotonating this hydrogen. It'll come from a deprotonation and protonation of the enolate. Similarly, we can exchange all of the hydrogens on this methyl. And we see that this double bond does move to become into conjugation with the carbonyl. So if you were looking at this problem and you came to the answer of D, but you didn't know why the double bond moved, it can actually be in either place, but thermodynamically it prefer to be in conjugation. So again, we still need to have a pKa that's sufficiently low for it to be deprotonated by the base that we're using. Yeah, I think, or at least I was hoping when making this that there are two parts of A that would be sort of no-goes in this. One is that this proton does have an exchange, and there's no way to put the negative charge there. And so since we can't deprotonate this one, and it shows an exchange, that's something to sort of rely on. It's not within our resonance arrows. So if you draw this resonance out a little bit further, you can also put the charge on this carbon, but it never ever gets on that middle one. And along the way, we showed how we intermediate, in the practice problem, by exchange. So mainly these are in equilibrium. So formally, it's a deprotonation redeuteration. So the hydrogen gets exchanged for a deuterium. Because they call it more of an exchange because it's just an isotopic switch rather than like a proper transformation. That's usually what people say. Number 7 was one that I was hoping this would actually have a higher ranking for, I guess, mainly two reasons. One is this is a question which actually you shouldn't try to rationalize through. Each of these are red box pKa's from our original pKa table we were supposed to kind of have in our minds for reference. So I thought that either one, you'd be able to put a number onto each of these from what we had referenced, and then come to the conclusion of C, or recognize that at least, oh, I'm supposed to have these memorized, and then maybe go to the sheet and look at it since it was open note. But since we chose them from the red box, these are the ones that actually sometimes are difficult to distinguish between. But I think maybe a lot of people either didn't have the dimethylmalonate pKa memorized. Perhaps people who were had these numbers in their head would be able to do more quickly. I think in the end I over tricked everyone a bit. And number 10, this seemed to be a problem that, again, I mean, more than half the class got it right, but just to kind of reinforce some of these trends. And I know that it's also led to me definitely going and making the acid-base sort of review to hopefully highlight some of these elements. And I think if we look at the different pKa's, we can see that we have a 1,3 dicarbonyl. This should be the most acidic because we know that it certainly will be more acidic than C, even if we don't know what the amide pKa is. Things we've talked about in class quite a bit are aldehydes and ketones. We say have similar pKa's, though usually aldehydes are a little bit lower in pKa. But we know that esters are less acidic than ketones and aldehydes. And this gets us down to a discussion between A and C. And this also kind of correlates to, or we have to be able to recognize why A is less acidic than something like D. So why is an ester less acidic than a ketone? And it comes back to this resonance argument. I've been trying to think of different ways to explain this because I think the ground state explanation maybe is not. You can use maybe another way to think about it. So if we deprotonate an ester, we can make an enolate. And this enolate stability is really dependent upon having this oxygen with a negative charge. And the more that it's able to stabilize that charge, the better. Why did we throw B out? So I think across the board, all the 1,3 dicarbonyls are always much more acidic than the single carbonyl variants. So there's two ways of looking at the NR group. So if we're talking about this hydrogen is going to have a very, very high pKa. This is going to be a little bit more than 36 from our ammonia reference. And that's because we're putting all this negative charge on the nitrogen. In the case of B, if we draw out that conjugate base, all of it's you never actually put the charge on the nitrogen. You're able to put the charge either on this oxygen, on the carbon in the middle, or you can push it all the way to the other oxygen. Since you're sharing the charge between two oxygens and a carbon as well in this sort of very delocalized pi system, this becomes a very stable conjugate base, especially relative to something like C. So we don't know where B is relative to like a 1,3 diketone. We know that it is, or we don't know the actual number, but we definitely know that it will be more acidic than something like C that only has half of this resonance stabilization. So while true that amines are not basic, we don't want to go and make necessarily jumps of just seeing more nitrogens and thinking it's going to be less acidic if it's not a hydrogen directly on that nitrogen. And so whenever we go and deprotonate, say, an ester versus a ketone, another way you see this described sometimes is competitive resonance of the conjugate base. And since we had this lone pair on this oxygen that was donating into the carbonyl, and this led to stabilization of the ground state molecule. Esters are lower in energy and less reactive than ketones. We can also draw a resonance isomer where we have the methoxy in this anion. So this is our next best resonance structure. So it's trying to create a resonance structure somewhere. This leads to actually a higher energy conjugate base because it's more now has more electron density on this carbon. Not only do we have sort of donation from this oxygen here, we also have donation from this oxygen here. This makes it very nucleophilic and then very basic. And if something is more basic, we know that its original compound has to be less acidic. I always thought this is a little bit harder to see or kind of make sense in your head because it still goes against the sort of idea of more resonance structures doesn't always mean more stable, because the effect of the oxygen on this double bond actually leads to a higher energy double bond that will be more reactive overall. The original way I like to think about it a bit more is that this resonance interaction over here on the left, this one is helping to keep the molecule stable, and whenever we deprotonate it, this methoxy group now doesn't have the same stabilization onto that oxygen. It now has to be able to use this carbon, which is a really poor acceptor for the electrons, that now creates a penalty upon deprotonation. But if you remember that somewhere along the way, I guess, that the reason that esters are less acidic than ketones is that they have this resonance stabilization. Amides have even more of this resonance stabilization because nitrogens are less electronegative. And this means it's going to have an even larger barrier to overcome for deprotonation, because it was very happy to have that carbonyl all to itself. And now if we go and draw the analogous types of anions, we're actually going to have an even more basic and more nucleophilic conjugate base as a result. And the last thing I want to mention is this synthesis problem. So though this is where we needed to use aldol reactions to build up a molecule. So you can see we have 3 different parts of this molecule that we can attribute to the acetaldehyde starting material. Probably the first disconnection you want to make is breaking this bond between these two, because this is our standard aldol addition reaction. We can see that if we can make this linear 4-carbon aldehyde here, we can do an aldol addition into the aldehyde and get the product after workup. Note that you would have an unselective crossed aldol reaction if you didn't make this enolate on the left using LDA. So this is how you will be able to get selectivity on that last step. I think we took 1 point off if you didn't use LDA and just use something like sodium hydroxide cold. And now the question is, how do we get rid of this double bond? Or how do we get rid of, how do we build up this aldehyde? And there was a couple options you could have done. I put another one on the solutions. But the easiest way is to just do a aldol reaction with heat. This gets rid of the oxygen, and then palladium on carbon to hydrogenate. The little aldol sheet that we had in the reaction summary at the very top, that could have potentially been useful here because it shows how you can get to these different sort of carbon skeletons from aldol reactions. The one thing I wanted to mention, though, is some people tried, and there are some reasonable solutions that can come through these molecules. They're a little bit longer, but some people ended up getting molecules, these 1,3-diketones, whether it was an acid or an aldehyde or some other oxidation state. And they were attempting to react these with LDA. So LDA is our big, bulky, super strong kinetic base that usually will deprotonate the least sterically hindered hydrogen of a ketone. But one thing to do note, and I don't think I made this clear, so I didn't take off on the exam for this in some circumstances, is that if you just have a hydrogen that is just way more acidic than another part of the molecule, LDA's steric bias and preference will only really come into play when we have two molecules of two hydrogens of pretty similar pKa. Since this one in the middle here, or actually let's use this as an example. Since this one is going to be, around 9, where the one over here is probably closer to 19, it will definitely go for, how do I get rid of that? It will definitely go for the high, I want a different color. It will go for the more acidic hydrogen first, even though it's a bit more sterically hindered. So the steric preference usually comes into play just if they have similar pKa's. In the top example, we actually have 3 different types of hydrogens to look at. And this carboxylic acid, now we're adding that to the mix, this is going to be around 5. This is definitely the most acidic, and really this is probably the least sterically hindered. But I think if someone tried to use LDA on an 1,3 dicarbonyl with an acid, I think we took off a point. If you did it on a 1,3 dicarbonyl that didn't have an acid, we didn't take off a point because I don't think you had the information available to you to know that. So I didn't count off, but just because it was correct on this past exam, I am trying to correct for that here and now. So please do not do this in the future. How did we get the first step where we went from the aldehyde with the methyl to the aldehyde with the ethyl? So are you talking about this step? So if we use sodium hydroxide and heat, our initial reaction will be, we have an aldehyde. We, under basic conditions, will make the enolate. This will attack in. After proton transfer, I'm just going to draw that. We're going to make this aldehyde. This aldehyde can be further deprotonated. And then do the E2 elimination. And that gets to the aldol condensation product first. I think part of it is recognizing that in this, if you have all 3 of these carbons in a linear fashion, somewhere you're going to need to have 2 different aldols bringing these molecules together to get that correct orientation. All right, so those are the main things I just wanted to mention that I saw as maybe either things you needed to know or things you may want to have some more background on. Are there any other general questions for me? LDA will be selective for a ketone over an ester because the ester has a higher pKa. If you have an alcohol in a molecule, I would not use LDA. We'll definitely go for that proton first. The red hydrogen is just a carboxylic acid. So that's not even an alcohol. This is since it's in conjugation with the carbonyl, it'll be a carboxylic acid. So all those are around 5, plus or minus a pKa. Maybe I'll make a note here. I guess the note is LDA requires I'll phrase it this way. As steric preference for hydrogens of similar pKa. On the reaction summary sheet, I think I made a similar note along those lines. So if there's no more questions about the exam, or if you do, you can probably check out the video. Hopefully that's useful. Are there any other general topics from any of the sections which you want me to refresh or something like this? I already kind of put what I thought is the most useful on those summaries. But if you have further questions about some of the material there, we technically do not have class on Monday. That is, we're not supposed to have any instruction on that day because it is like a reading period. So we're not supposed to have a formal class. I will have the office hours on Wednesday and Thursday evening. And similarly, if you guys have questions, please post them on Piazza and just say discuss at office hour, and I can take care of it there. If you don't specify to discuss at the office hour, then I probably will just reply on Piazza with words, maybe a picture if I have time. What are the different ways to make epoxides? So we only have one more, and then I think I got someone send me an email that they probably are requesting for me to review something. Go to our handy review sheet. I think I have it on here. Ah, there we go. The epoxidation section. These are our methods for making epoxides. Actually, there is one more. It's in the review sheet. You can either use MCPBA, or you can use the basic peroxides, where it does a 1,4 addition followed by a rebound. The last way is a fairly specific scenario where you have a leaving group next to an alcohol, and you add in even something like hydroxide. And this will be able to go down and kick it out to make the epoxide. All right, yeah, we can talk about the Wittig reaction. I think, let me check my email. And I can address this by going to just the general solution. So someone wanted me to talk a bit more about the exam 5 mechanism, and I can review that real quick. I talk about it in the video a bit, but the main features we want to recognize here are that we don't have very good nucleophiles or electrophiles at the beginning. We have enols. So we have an enol present, and we have an alpha beta unsaturated dicarbonyl. So in order to get these two to react, we need to have one of them be activated. And so this is where we go and we look at the reaction conditions, and we see that it is HCl. So this is not our normal base catalyzed mechanism that we normally have written out. So this is where we're going to need to make a bit of a leap of our understanding of all the other carbonyl reactivity we've seen under acidic conditions and apply it to this situation. Excuse me. And so whenever we look at what our electrophile is, that is what we want to protonate to make it more electrophilic. So we're going to have the lone pair of the hydrogen protonating this oxygen. This allows our OK nucleophile to react directly with it. Afterwards, you'll see that we end up with a positively charged oxygen of this carbonyl, and we have an enol on the other side. Note that if you did not protonate this initially, you would end up with an O minus. That would be very unreasonable to exist in under basic conditions. And then essentially it's just proton transfers to get you back where you need to be. So we're going to need to protonate this enol carbon, deprotonate this oxygen. So I did that in just one step with a proton transfer. And this chloride will be able to come around and take this hydrogen back. So going back specifically to if you are simply moving a hydrogen from one part of the molecule to another, then you can write proton transfer. Absolutely. That ever since I think for the past 2 exams you've had that liberty, but you do need to use it correctly. So this is one of the things where you could have a lot of equilibria taking place. So it is possible that you could protonate that central carbon. But this is still going to be in a reversible equilibria. This doesn't give you the nucleophile you need to have it react with the right carbon to get us to the product. So there are things you could do. Part of it is recognizing what is my nucleophile, what is my electrophile, seeing the bond that needs to be made, which is this one. And since this enone is the electrophile, our enol or enolate is always going to be the nucleophile, I chose the protonations that will be productive to get to the product. There are other things that could be taking place. This protonation would be one step towards doing enol tautomerization. Let me make sure I got these. We could do the... and so on this question, there were, I guess, 2 ways that you could have used a basic mechanism. One was where you actually deprotonated the original compound and made the enolate anion and then added it in. There were some people that used a neutral enol and just didn't pre-activate the 1,4-dicarbonyl. So we graded those slightly differently. Of course, if you feel that something was graded unfairly or unequally, I will be happy to take a look. You can request a regrade, and we can take a look. I think I've already received a few. The Wittig reaction. Let's talk about the Wittig reaction. If we're trying to open an epoxide under acidic conditions, actually I can address both of these by going to the, I think, topic review. So if we go to acidic ring opening, yes, it does happen. Under acidic conditions, epoxides open at the more substituted. And this is really because it's the carbon that's better able to stabilize positive charge. So rather than think about it as the more substituted, sometimes it's better to think of what would make a better carbocation. But the Wittig reaction, that's why I came here. The Wittig reaction is fairly general. So in terms of scope and limitations, I don't think we had too many of them. Mainly, you can get it to react with pretty much, as long as you make the ylid properly. So the ylid is where we end up deprotonating this hydrogen. And we use sometimes kind of funny bases like phenyllithium that we usually think about doing nucleophilic additions, but they will deprotonate much faster. We're going to have phenyllithium attack. And you can either draw this in the doubly charged form, this Zwitterion, or with this carbon phosphorus double bond. If we can successfully make this carbon phosphorus double bond or this ylid, then you can pretty much have it react with any aldehyde or ketone. It does not react with esters or carboxylic acids. So I think those are our 2 limiting cases. The other variant is the Horner-Wadsworth-Emmons reaction. This is the same way, usually a very similar type of reaction. There's not a lot of times you would want to use the Horner-Wadsworth-Emmons reaction over the Wittig. I think if you know the Wittig, you're probably pretty good, but it would be good to know this reaction in case I ask a question specifically. The first step is the Arbuzov reaction. That's a mechanism. I don't know if we may have had that on a test. I can't recall. And it's a similar way where now we're going to be able to deprotonate this alpha hydrogen. We usually don't need as strong of a base because we have this electron withdrawing group right next to the ester. It's kind of like this will be similar in pK to a lot of our beta keto carbonyl compounds. And this will do the similar addition into the aldehyde, making a 4-membered ring intermediate. And in the notes, you can see we drew out the equilibria. A lot of these steps are more reversible than in the proper Wittig reaction. So we end up getting E isomers preferentially. They want to be on the or a trans type double bond. So I think these are the main points to remember. So don't use it on an ester. Don't use it on a carboxylic acid. Deprotonate your phosphonium salts with strong bases and add it to a ketone or aldehyde. I think those are the main points. So we go over multiple choice 2. Okay. C versus A. So C does not have any enolizable protons. So there's just not really an enol anywhere. So part of having an enol is the all part, like because ene is like alkene, all is alcohol. We need to have this OH. Oh, B versus A. This really doesn't have a whole lot of logic other than the driving force of aromaticity is much stronger than just the driving force of that hydrogen bond. So going from B to A, I think this was the case where this in our notes was fully shifted to the enol form. So we never really draw a phenol as this isomer. We see it occur very briefly in the Claisen rearrangement, but it quickly tautomerizes back to the phenol. Yes, A is the keto form of a phenol. So if you were to imagine moving this hydrogen over to the oxygen and doing the 2 steps, you get phenol out. So that one will exist completely in the phenol form. Any more questions? But yeah, these are the solutions if you haven't seen them yet. 3 was the Robinson annulation. We just had some new substituents on them. 4 was a combination of 2 reactions from the notes where we had our aldol condensation under acidic conditions and then the nickel hydrogenation that reduces both the CO and CC. We have a cuprate addition that does not add into either of the carbonyls because cuprates never do 1,2. B is a pi to pi star transformation. 7 we talked about. 8 has 2 steps. One is knowing the reaction of the dimethyl cuprate with an acid chloride to first give a methyl ketone. The second is recognizing that the second step is the haloform reaction. This will get us to our carboxylic acid C. If you were trying to decide if Friedel-Crafts, or actually, it's not proper to write Friedel-Crafts, this should say EAS. if electrophilic aromatic substitution would take place. Then we can kind of look at the different possibilities. The only one that has the haloform product and an iodine is B, and we know that if it did do EAS, it would not go in the para position. So hopefully that will help you get us down to just C is the answer. For number 5, oh yeah, you would only need to have one equivalent of dimethyl cuprate. Sometimes people will still add in excess. Sometimes these reactions are a little slow, so they'll add excess reagent to make them go faster. But no. Mainly this was just saying if you did have more of it around, would it do anything? The initial product also would end up being this enolate, which would further make a second addition take place even more difficult. So it doesn't happen even with the neutral compound, and so adding a nucleophile back to an anion would not happen. 9 was similar to some of the cyclization questions we'd seen. So again, it's kind of testing, are we able to properly be able to count the cyclization starting from the enolate carbon to one of the ketones? Choosing either of those carbons would give you the same result. And it makes a 5-membered ring in the end that then gets methylated with methyl iodide. Talked about 10. For 12A, we just do LDA with an alkylation twice, so the second will go on the opposite side from the first alkylation. For B, we had an aldol reaction, crossed aldol with a non-ionizable partner that retains the alcohol at the end, so we're going to need to have the reaction cold. We also accepted LDA for an answer here because it can only deprotonate those methyls. There aren't any acidic protons on the other component. Enamine acylation. The carbon of the enamine is nucleophilic. It will attack the carbon of the acid bromide and then collapse to give an aminium that then hydrolyzes on workup. Quite a few people had trouble with D, so recognizing the disconnection to get us back to an aldol condensation precursor. So the process is, first we need to imagine going backwards from the E1CB. This gives us this tertiary alcohol. Then imagining how this tertiary alcohol could be made from an enolate addition. And now it'd come from breaking the bond between the tertiary alcohol carbon and the carbon next door. That makes this enolate with this ketone. And so we just need to start from the keto form of this enolate, which is the structure shown in the box. Some people were sneaky and clever, and they just drew the E1CB precursor. That was, I couldn't say that wasn't correct. So it was not the answer I was looking for, but it was also not correct. So you got me this time. We talked about this. Oh, we haven't talked about this synthesis question, but this was quite similar to the one that was on the problem set. So also recognizing that this is going to be a malonate ester synthesis, we see that we have the methyl iodide and the ethyl iodide appear on the molecule in those two places. Then you go through the synthesis, you can switch the introduction of methyl iodide, ethyl iodide as you want. The only maybe twist is that upon hydrolysis and decarboxylation, we do have a carboxylic acid left. And so this methyl iodide actually comes back again to rejoin as the methyl ester. We talked about B, and we talked about the mechanism. Cool. Well, I think that will probably be all for today. Again, please, as you start to review, look over things that are unclear. If it's just a general topic you want me to discuss again at an office hour, I will make sure to cover it, and then they'll be posted to YouTube. If they need to last a little longer, I can manage that, so long as there's still questions for me to cover. But please go and put your recommendation on Piazza so I can prepare for it ahead of time a little bit and work through these problems. Yeah, I'm gonna make it, the extra credit will be Wednesday at midnight. If you personally or someone has a problem with this timeline, since I originally said you could turn it in on Friday, just let me know. I mainly just want to be able to post the solutions without people then going and just looking at the solutions, copying them, and putting it in. I would like to have some effort in. And I would say that if you submit an extra credit that has some errors, we're not going to grade it. You'll still get the extra credit points. I just want to make sure people. Oh yeah, I just want to make sure people are able to have some time to work on it, learn from it, and hopefully do well on the final. Alrighty, everyone have a nice day.